Okay. So, any questions? Jesse, do you have any questions about it? I mean, we are going to kind of talk about it at the beginning here of the lecture about kind of type checking versus type inference. And you're doing type inference. You're taking a context and a term and checking that the term really does have a type. So let's look at that. And I'm really, this is insane. I have no idea why these notes are not. My Wi-Fi is on my, I mean, I have to turn my Wi-Fi off on my iPad at home all the time. It just uses up so much. Wi-Fi is on. I'm hooked up to UWYL. Why would it not mail? All right, I don't know. It didn't come. So let's look at you know, what I had put in the notes which does start off, and then if you get a more specific question, maybe you can ask me. Is that okay?
Yeah, that's good. Thank you.
Okay, so now what's going on? Oh, geez Louise. Okay, looks like I'm gonna, yay. Okay, so you know, I'm going now from this discussion here is based on what's in Mimram's book, and it's section 4.61. Oops. What is going on here? Let me make sure that my Bluetooth is, this thing's not connecting. Could it be connecting to this? Wow, that's one thing about trying to move to a new place. All the technology doesn't work quite the same way. Let's see, I want to go over here and I want to maybe turn off Wi-Fi and turn off Bluetooth. So that thing is disabled. And my Wacom tab is plugged in. I'm so glad we're recording this for posterity. wonder. All right, I'm going to stop sharing for just a minute and see if I can figure out what's going on here. Okay. All right, let's see if we can start over again. I apologize. Okay, so we're looking at MemRam's presentation, and it's page in the book. I'm not sure if the book pages are different, but it's MemRam. Oh, come on. I want the drawing. Why is it? It's like it's. All right. I don't know. Maybe I'm going to have to stop share. It says that I'm connected. Does anyone have any idea why my Bluetooth connection would be? It feels like it's there, but it's just insanely slow. It's like there's a huge lag.
Do you have a new Mac update on your computer or your iPad, or are you using a Mac?
No, I'm not actually. I'm using Linux. I'm running Linux, and I've got a Wacom tablet that I've been using all along here.
Oh, okay. I know the update's pretty bad, but
Yeah. Hang on. All right, it's telling me now that this device is successfully added. Let me try one more time before I give up. Okay, that's working now. If only I can get the pen to work. What is it doing? Oh, that is so weird. All right, I'll have to, what I'll do is it may actually almost be better, although I can't draw pictures as well, but I thought everything would work so much better here. And I think Zoom works better for sure. I've been on Zoom meetings earlier this morning and it worked great, but okay. All right, let's try this. Okay. Oh God, I really am sorry about this. Okay, so there's kind of there's type checking, there's type inference, and there's typeability are three kind of different ideas, but they're all very closely related. So type checking is if you're given a context, call it gamma, and a term, so a lambda term t, and a type A, decide whether gamma, I don't have a good turn style, but kind of the best I can do is gamma t. Gamma shows T has type A. So you're given something like this and you're given the gamma, you're given the term, and you're given the type, and now you want to check whether or not this is true. And so the way to do it is to try to build a derivation and see that if it is true. Now, it turns out that we're going to have a really interesting theorem that says that uniqueness of typing. Can you read this?
Yes.
Yeah.
Okay, good. All right. So the theorem uniqueness of typing is very powerful because it says, given a gamma, a t, a term t, there is at most one type A such that gamma shows that, under gamma, we can show that T has type A. And also, so that's pretty powerful in itself, but there is at most one derivation. So we haven't really had time to go over this. Is my internet lagging? I don't know. Hello?
We can hear you, sir.
Yeah, we can hear you well.
Okay, it's interesting though. I'm looking at myself on the screen. That's like way behind. Why is my internet lagging so much? Or why is my video lagging? I never do use this camera on this thing, but maybe it's like too high a resolution or something. So anyway, this is a pretty powerful thing. It's saying that, look, if there, there's only one type. So in other words, like the program that you're building for homework is doing type inference. We'll come to that next, where you're given gamma and T, and you have to generate A, the type A. But the amazing thing is that if you're able to build a derivation showing that gamma TA, that T has type A under gamma, then there's only one derivation. So that's a very strong property about the derivations that we're building. So for type inference, you're given gamma, the context, and the term T, and you want to show, the problem is essentially to decide whether to find T. Find the type A. Such that gamma shows that T has type A. And then there's a typability. And that is a question that says, given gamma and T, decide whether T admits a type using gamma. So once we can do any one of these, we can kind of do the other ones, right? Especially because of this extremely powerful theorem. So if you want to type check something, what you can do is you could do type inference. So you're just given gamma, T, and A. You're not given the derivation. And the only way that we know that gamma turnstile T colon A holds is if there is a derivation that shows that. So what you could do is, because of this strong theorem, you can take gamma and T, find A, and then check whether your A is the same as this A. And if it's not, you say, decide means answer yes or no, true or false. And the answer then would be false if the A was different, because you've got the only possible A here because you build the derivation. Or you can do this, and it could be that your program is going to return nothing. And in that case, what does that mean? That means that there is no such derivation. let me just see something here. I mean, I'm finding this extremely strange that my video is so far is lagging so much. Because I'm actually plugged in to the network here. I'm not even on Wi-Fi. Anyway, so these are kind of the three questions. Now it turns out that that you can find linear sized algorithm, a linear algorithm, and linear in the size of the term t. To solve all three problems. And that's what one of your homeworks is. You're writing the type inference. You're building the derivation which shows that this holds. So in the process of building the derivation, you're also finding A. Yeah? Now, he gives the proof in his book Mimram, showing that uniqueness of typing holds. But one thing that I'm not sure, I mean, I've been like skipping around and trying to put some of the material together because he presented logic first. So anyway, so I've been jumping around, but I'm not sure. Did he show that, for example, not all terms are typable? Some of them don't have a type. Oh God. So what's an example? Can anyone tell me an example of a term that you don't think would have a type?
The identity.
No, that's let's do that one. That's a good one to do. So we want to show that, starting with the empty context, we want to show that lambda x dot x has some type. And the rule says, I'm sorry, we're working in the notation where we have to label the variable with the type of that variable, right? That's what the language has. Maybe I should write down the language first really quick. It's like lambda terms are just equal to variables, or they're something of the type m applied to n, or they're of the type lambda x, and I'll put since I can't superscript it or whatever, I'll put it in the squirrely brackets, m. And so remember, x is a var, m and n are in lambda, and a is in the language of types. And so we have to also give this language a grammar. And so types are either equal to, I'll say, A or T arrow T2, T1 arrow T2, where A is in a collection of type vars and T1 and T2 are in the language of types. So, I'm always tempted because, to write for the untyped lambda calculus, we write this. But in the typed lambda calculus, you have to label the thing. So if we start off with that, and what we're trying to do is figure out what this is, but we have to do the derivation. And I don't know, should I write down the rules? One rule is that gamma turnstile x colon a, if and only if the pair x comma a is in gamma. Right? Gamma shows, I'm going to need another line. Gamma shows that M n has some type A if, and you're like, you're all there in amazement. How does Caldwell remember all this stuff? I forget everything. The reason I remembered is because it's easy. It can't be any other way. I'm re-deriving it as I'm going along. I'm going like, well, all right, now what does it have to be? Oh, it has to be, certainly, if I'm going to show that this applied to this has type A, I'm going to show that M better be a function because I'm applying it to something. And so it better be a function whose input type matches N. So I say, okay, gamma better show that M, and since the resulting type is A, this has to be a function, and I know that it has to return an A. And so let's just call it B. And then gamma turnstile, this better be, N better be of the correct input type, B, right? That's what it has to be. Are there any questions?
How are you checking that like X, A are in gamma if you don't have A?
Good question, because that's part of your homework. How to find that A is you have to look through gamma and find the first X. Now, if you're doing, in the code that we wrote that I gave you kind of as a basis of this, I switched the, he has the newest value on the right side of the sequence, the context sequence, the gamma. And I put it on the left because that's the most natural thing in the world to do if it's a list, right? So suppose, I guess I should say, okay, and gamma is, it has type list of string type. But we just called it T here, right? So gamma looks like, suppose, let's go down here and I'll just, because I'm still doing the rules, but like suppose gamma is some list and it's got like an X, A. Of course, you know, in your actual code, it's going to be something like the string X and the constructor tvar applied to A, right? But I'm just going to write XA instead of writing out all those things. But this has to be a type. And so that means it has to come from your language is a little bit more complicated, right? Because you have a tvar string as the constructor for type variables in the Haskell representation. But let's just say it's XA. And then even suppose it says X comma A arrow B. So that could be your gamma. And the key here for us is that the newest entry or the most recent entry is on the left, unlike what Pierce did. So now if I'm trying to, I've got gamma, so I've got, you know, this thing. And I'm trying to show X has some type. And so what do? I start looking at the list from the left side. And suppose I might have even something else in here. I might have a Y has type A also, for example. And so I start looking from the left side because I'm adding to the left. And I say, okay, did I find an X? No. Okay, did I find a X? Yes. Then that has to be the A that goes there. So this is the only derivation, given this context and this variable, there's only one derivation. You might think, oh, but look, X also has the type A arrow B, but X can have only at most one type. And that's what the context is doing. Okay?
Okay.
So you want to look from across the list. And I mean, you know, I don't know. I mean, there's quite a few different ways to do that, to accomplish that. There used to be, I don't know, maybe there still is. I mean, I'm sure there is somewhere. There's a function called assoc, which looks through a list. This is called an association list. And it's associating Y with A and X with A and X with A arrow B. And assoc actually is a function that probably exists in the Haskell library somewhere, though. It's something like you got to load like data.list. Maybe it's just data.list. Keegan, do you know?
I don't know, but I think you gave us a function that does that.
Okay.
By context or something like that.
Uh-huh. So anyway, that's a little proof. This is a proof that X has type A in when this is gamma. Now, in this one, I want to show that the application has a type. Well, it better be. I mean, I don't know. This should just, you should be looking at this and going like, ah, of course. Or even better, why is he saying this over and over again? It's obvious. Please tell me that. Suppose I call this F. Does that look more familiar? Oh, the function is called F. And then what if I call this X? You know, the names don't matter as long as they're actually names from terminal variables. Maybe that makes more sense. If I want to apply F to X and get back an A, it better be that F takes something, some kind of input, and X is the right kind of input, and then F of X returns B. All right, I'm going to beat this dead horse a little bit more until somebody screams and hollers and says, please stop. What if, you know, suppose F is something of type, you know, int, arrow, int. What is the type of F of 7? So
Int.
it's an int,
Yeah.
of course, right? Because I give it an int and it returns an int. So when I give F the int 7, this thing here has type int. Okay, maybe I'll count that as like, don't beat this dead horse anymore. But that's all that this rule is saying. Except that you might need to remember more things. Like you might need to remember, like you could have in the context, okay, F is an int arrow int, and now show that F of 7 has type int. Well, now I got to apply this rule, and I'd have to show that, you know, using this context, that F has type int arrow int, because the rule says it has to be a function, and then it better be that in the same context, 7 is of type int. And now we know the rule holds. Oh, and what is this rule? This rule is called AX. This one's called app. Now, I switched MemRam's versions around, and I really apologize. This is also called arrow elimination, and Simon, scream at me if I did it the wrong way this time. So the final thing is, so in MemRam he calls this oh, and I think Pierce calls this var or something like that, the var rule. But MemRam calls this AX. This rule is called AX. And finally, we've got the abs rule one more time. This one is called arrow introduction. And so the thing is that if we wanted to start with some gamma, and we want to show that a lambda x of type A T has some type, and it's going to be, because of that type flag there, I already know it's going to be this, but I'm not maybe sure of what the return type is. And so then I go up here and I build a derivation, but now I have x colon a const on to gamma. And I have to show that T has some type. And it doesn't have to be actually a variable. So I don't want to say B here. I don't know. I haven't actually been, maybe have I been making a mistake here? This doesn't have to be a variable. Well, it's okay to make it a variable because then I can substitute in any instance that I want to. All right. I'm going to look really quick in memram to see what he says about, if he says anything about that. I think he just uses capital A's and capital B's as he uses X for type variable and A and B in his language up here. He says X. And so we got to say X. And then here's where he uses A and B for arbitrary types. Okay. Okay, so here's the rules, and here's like an instance of a proof. We're working on this proof, and this one's just true by the axiom rule. Whoops, I want the middle line. This one's just true by axiom. And, you know, we'd have to add, obviously, rules. If we wanted to add integers to our system, we'd have to say, you know, we'd have to say like, I don't know, we'd have to add some kind of rule for ints. Now, I get nervous that when I've done this, I've done something that to me seems like really obvious, which is I just sort of said, okay, in my head, I said, let's change the language of types to also include ints. And let's change the language here to include numerals. And then, you know, we can have a function that tries to turn a numeral into an int, and then if it is, then this proof would work. This rule here, int, would be like an added rule that would say, you know, I've been putting the names for these on the left side. Dreaded insert mode. And I'm still in it. Stop. Okay. But let's look at this one. Oh, well, let's go back to Simon said, what about the identity function? Well, so now the rule, and I can split my screen so I can go back up and show you the rules. Here's the rules. And the only rule that applies is this one. And so I know this is going to be an A arrow something, but I don't know what. And then what I do up above is I change the context by adding x:(a) to it. And now I got to show that x has type. And when I look in here, the variable rule says the only type that it could have is A. So that's an instance of the axiom rule. And this is now, I take this type down and I see that, okay, the resulting value has type A. So in fact, the identity function has the type A arrow A, where A is any type. Is anyone there? Oh no.
Yeah, this is making sense. I'm just trying to understand some things, but like I'm going back and forth between like looking at what you have and my assignment and changing things too. So
Anyone else? All right, I'm going to show one more thing. I'm going to go back and show that. Oh, not that. I don't want to show you this. Let me just see if it works though. You know, some of you may actually prefer the typing. I don't know. Maybe is it clearer and when I'm doing it in Emacs?
I prefer that way because like to someone who doesn't have the central vision, like I always lost on your node most of the time.
Uh-huh. Okay. Don't go away. I want to stop sharing, but it's like, I don't know what goes on with this thing. Okay, stop share. And then I want to share my real screen. Okay. So this is the typing that Simon asked for to show that but now what about, and you know, you could try calling your program on this and should return nothing. But what about what if I start out and I say, okay, what about lambda x a dot x applied to x. So I'll put parentheses around this so it's clear. So what's the type of this? Well, it's going to turn out that it can't be typed. Because let's try, we say, okay, suppose x has type A And then I got to show X applied to X has some type. Okay. So now the rule, so this was the arrow introduction rule. And now I've got an apply, so that's the arrow elimination rule. And that one says, okay, from X colon A, show that X. And now the only time that I can show it, I have to show, the only type I can show it is that it's an A. But for the app rule or the arrow E rule to hold, this thing over here has to be a function type, and it's not. So now the other side works. This one's good because we could have, if we could have shown that X was something like, you know, A arrow something, then we'd be okay. So this is like a splat. We can't do what we need to do by pattern matching against the rule. We can only say that X is something of type A, not that X has any other type. So here we're okay. But this rule, even though the ax rule would apply and make us say A, that's not what we need there. So up here, we've done something like, you know, broken. Cannot, you know, can't complete. So you might say, oh, well, wait a minute. That's just because you started out with the wrong type. Like, what if we try doing this again with a different type? I'm going to say, what if this had been a function? That's what I needed it to be. That's why that proof failed, is because this thing needed to be a function. So let's tag X as A arrow A. And now we're going to try to figure this out. And so up here, we got this is an A arrow A, and then good, X is an A arrow A. But here, we're in trouble because X is an A arrow A here. And so this one's broken. This one's good. Wow. But this one here has this problem. Now, so we can't figure out this. This is, you know, this is like undefinable unless it's undefinable. Well, we could say we know it's an A arrow, but we can't finish the type. So this is, undefinable. So this proof didn't work. Now, you might be really like willing to bang your head on the wall a lot. And then you could say like, well, wait a minute, I know what's going on here. I need something else. I need, let me grab the whole thing. I need this to be, if this is an A arrow A, then I need this to be A arrow A, where this is A arrow A, and then my input maybe you think it's this. So X is expecting some kind of input, which is a function. Well, then that means that, so if the input to this thing is a function, then I'm gonna have to have X be a function that returns a function. And that would be kind of okay if this X was an A arrow A, this X was an A arrow A. But really, this way lies madness. Because I'm going to get kind of the same problem up here. Okay, and so then that's good. Okay, I got this as a function of the right type. Or at least it's a function. So that actually looks okay. But this other side is going to break. It's not going to give you the right thing. It didn't, there's no way. I need it to be an A arrow A, not A arrow A. Okay. So we've tried 3 different ways and we couldn't type it. And I don't know. I mean, if you write this down, the only thing that you could do is maybe try to fix around A. Now, here's a crazy thing in Haskell. Oh, let's see. Haskell, so we want to be able to write something like, I mean, suppose, I mean, we were kind of on the right track here, right? Is to say, look, okay, oh, this should be 2 x's, right? That's x applied to x. And that's x applied to x, that's okay. And that's x applied to x, that's okay. I'm missing an arrow here. So an interesting thing is that this is kind of like the right type. So it's kind of like if I said, I gotta, I really just wanna, if I say let ID equals \x arrow x in ID. So what is the type of this thing? Well, I'm applying the identity function here to the identity function. So this one has to have, now if I take that thing and I say, oh, take this thing and apply it to 7, I get back 7. So that means that this identity function has a different type from this one. When I apply this one, I'm applying an A. This one has to take an A arrow A arrow A arrow A. And then this one has to take an int arrow int. Now, strangely enough, in Haskell, the form let x equals whatever, some t1 in t2. On Haskell, this thing here is polymorphic. T1 can have lots of different types inside of T2. But it's also the case that, you know, in lambda calculus, they always say like, okay, let x equals T1 in T2. It's just the same as thing as, so it's equal. It behaves the same as supposed to, as lambda x dot T2 applied to T1. Right? These are going to do the same things. If I say like, okay, lambda, I'm in Haskell up here, so I should probably be using the arrow. But this T1 gets only one type is the kind of the point. So if let x equals, so I should be able to say, this expression here is the same as lambda ID arrow ID applied to ID applied to lambda x arrow x, right? So if let x equals T1 and T2 means take T1 as the body of a lambda expression and use the lambda expression to replace all the x's in T2 by T1. And it's kind of the same thing here, right? Replace all the x's in T2 by T1. So now I took this one and I can ask the type of this. And it's going to say, well, aha. And here's where it can't type it. It says it can't figure it out. There occurs check. This wants to make an infinite type where T is equal to T arrow T. Now, that's a weird thing because only the cognoscenti know that this is not equal to that. And why is that? That's because this let, they retype T1 in every context where they use it in T2. And so that's a kind of a type polymorphism that doesn't agree, doesn't work here. This X has to have two different types. And in the previous discussion, we tried to show, okay, we started out, all right, what if it's an A? And then we say, oh, wait, what if it's an A arrow A? Okay, what if it's an A arrow A arrow A arrow A? And the problem is that what we really want to do is to say A is isomorphic to A arrow A, and then we'd be able to do this. But you can't. Because here they only, excuse me, in the last one, in this one, they only try to type lambda x dot x one time. Okay. Questions?
Could you actually go back to the board for just a second?
Any questions?
No, not from me.
I really should stop doing that probably. Let's see. Oh, let's hear how this
Cognoscenti.
cognoscenti. I don't think I've ever used that word in conversation before. Okay. So no questions. Shall we take a little break? What time is it? Is it like we're a little late for the break, but we could take a little 5-minute break?
Sure.
Okay. I mean, I don't need one, but if is there anyone that doesn't want to take a break? Chat.
I need 5 minutes. I'll be
Okay.
back in 5.
Okay, good. See you then. Now my video's not lagging.
So I have a very weird question for you.
Hello?
Yeah, I have a question for you.
Okay.
So I don't know whether that is a good question or not. So you saw that lambda x dot xx doesn't have any type, right?
Right. Mm-hmm.
So like, is that is the part of the sigma we talked earlier, the way we do the recursion in the lambda calculus. So like, that's why like the recursion doesn't have type because of that. Any relation with that?
Right. You can't, right. Another thing that you can't give a type to is the Y combinator. The fixed point combinators that we wrote down don't have types.
Okay.
So yeah, it's kind of a problem. So then how do they do? They don't, I mean, but you can do, when you put it all together, let's see, let's go try. Um, But I think if I try to type down,
I cannot see your screen.
oh, I'm sorry. Oh, I'm sorry. Bu- bu- Okay, so here's a generic fix, like you just described this thing, fix of having the fixed point property. And it turns out that when I load this, oh, well, I'm in the middle of writing something else, but this loads okay and factorial works. Here it loaded. I looked at the type. Can you see this? I looked at the type of fix and it said, oh, takes a function from T to T and returns a value of type T.
Yeah.
And so you can sort of work out in your head that this has the right type. This has that type. And then you can use fixed points to write like the factorial. Take the fixed point of lambda fn arrow. If n is less than or equal to 0, then 1, else n time f time f n times f of n minus 1, right? And so then I don't know. I did the factorial of 11. Is it right? I don't know. Gosh, it's like 39 billion. No, what is it? No, I'm only in millions. 39,916,800. But what I was going to say is I don't think this one can type. Yeah, occurs check error. So this is kind of like a standard implementation of a fixed point in pure lambda calculus, but you can do it in Haskell by writing just this thing called fix that has the fixed point property. So this will not type. Okay?
Yeah.
That was good.
I'm back if you're waiting for me to start.
Okay. I mean, is everyone else here? I don't know. Is everyone here?
Yep.
So Zach's here. Kyle seems to be here. Jess, are you back?
Yeah, I'm here.
Okay. Keegan.
Yep, I'm here.
All right. Okay. So, I guess, my thought, what I would do next is go on to kind of like if Confluence is the or the Church-Rosser property is kind of like the fundamental theorem of lambda calculus. Then
So I don't want to interrupt, but did you start the video again?
I don't think I stopped it.
Ah, cool.
Yeah, I'm still recording. Where does he talk about this? He doesn't. He does. I know he does. Oh, here it is. Section 4.22 of MemRam. This is where he talks about strong normalization, 4.2. But the thing is that there's like an interlude in here with where he shows the Curry-Howard correspondence because they've already done logic, and so and then he uses that to prove certain theorems. So he proves using I don't know, we should probably go through or I should go through. I've never actually gone through this proof in full detail, but we don't really have time. I'm just looking for his definition of R sub A. Okay, these are reducibility candidates, which is Girard's proof used this idea, which is based on a proof by Tate. So the idea is essentially of strong normalization. Well, the theorem says that every typable term T will always end up on normal form after finite many steps of no matter which way we choose to reduce it. So, you know, we showed like, oh God, maybe I don't know. What am I going to do about this pad? All right, I guess I just can use my email. I don't know, I don't feel as good typing this stuff out, but strong normalization says that for every T which has some type A, well, maybe I should say one thing first. I should say that if a term T has no variables,
You're not sharing again.
Dang. If a term T has no free variables, then gamma can be empty. And so you remember what a free variable is? I mean, we could go back up to the syntax and we can write the free variables of X are equal to the list containing X, the free variables of V. If we had that extension to numbers, that would be empty because there are no variables in a numeral. The free variables of M applied to N is equal to the free variables of N union together with the free variables of N, and the free variables of X of type A dot M are equal to the free variables of M minus X. So they're just the variables that are not bound by a lambda that occur in a term. And so it turns out that if a term T has no free variables, then you can type it with a gamma empty. And, you know, if, say, if the free variables of T is not equal to the empty list, then the domain of gamma must be a subset or equal to the free variables of T. Maybe that's the easiest way to say it, right? Because that handles the empty case, which I gave specifically above. Because if the free variables of T is empty, then the domain of gamma has to be a subset equal of free variables of T. Oh, it has to be, I'm sorry, it's the other way around. Right? It's that the free variables of T have to be a subset or equal to the domain of gamma. So I don't know. I can't, it's hard for me to tell. I think, you know, when I'm in class, you know, I can look at and I can see like 2 people maybe out of a class this size that are kind of like clearly get this. And then, well, you know, I don't know how many of us are here today, 6 or 7, you know, 4 more are like, what? So, I mean, I don't know what to do. I could go through a bunch of examples, but it's really time consuming. So all this is saying that, you know, okay, let's see. Let's make a little theorem. If T is a term, then T is typable well, this isn't exactly right. It's not typable in any gamma that has types for those things. In some gamma, I guess maybe what I want to say is, if T is a term and T is typable in gamma, then the free variables are T are a subset equal of the domain of gamma. What do you think? Anyone care to explain what this is saying? Come on, somebody, like, somebody has to try and speak up. Does this theorem make any sense? Or is this just like so, it could be that we're like so deep in the kind of definitions that you don't remember enough things to be able to think about this.
It's definitely a little convoluted to me. I'm trying to wrap my head around it as you have it out there, but it's not like all like alien. It's some.
Mm-hmm. Keegan, tell me what this says. What does it mean to you?
It means that you have to have types known for free variables in a lambda term in order to be able to type that entire lambda term.
Yep. So, right. So it means like if I have a lambda term that says lambda x, I'll say a dot lambda, let's just say x applied to y. Okay, what are the free variables of this term? Well, if you do the calculation that I just said, it said, okay, find the free variables in x applied to y. That's going to be x and y, but then get rid of x because it's bound. So that's just equal to y. And so this theorem is saying that if T is typable, then gamma has to contain an entry for y. You cannot type this term without having an entry for y. And so we could see that by saying like, okay, let's try doing it in the empty set or the empty context. And so I'm trying to show that lambda x, which has a type, let's say a arrow b dot xy, and I want to show that this has some type of term. And I know that the type of this term is going to start out with an a arrow b, and then it's got to return something else, right? That we always know when we're trying to type a lambda term. So then the rule says, okay, add to the context that x has type a arrow b. and I'm getting that from here. So I say, okay, X has type A arrow B. I add that to the context as the most recent entry for X. And now show that, I don't really know much over here, except from the rule. I know the first argument has to be an A arrow. So, but anyway, so I have to show that X applied to Y has some type. And if I apply the rule for let me see, let me show the rule. The rule for application. So this is the abs rule, because I'm working with an abstraction. This one is, I'm working with an apply, so this is going to be an apply rule. And the apply rule says the first thing, X better be a function, and in fact, I know that X has something of type A or B. So this is a correct axiom instance or a var instance. But then I have to show, if that's true, then I got to show that assuming that X has type A arrow B, I have to show that Y has type A. But I can't do that. So here I'm broken. Ah! I failed here. But you could see that you're never going to have any hope of typing a term if there are free variables that are not bound by a lambda. When it's bound by a lambda, the lambda tells you what the type is because the lambda is labeled. But this thing has no type. And eventually I'm going to have to say, what is its type? And I get over here and the rule tells me, the app rule tells me that it has to have type A, but I have no way of showing it because I don't even have an entry for Y. I could have the wrong entry, which is why I had to be careful about this statement, because it's not just that as long as your context gamma has an entry for Y, that's not enough. It has to be the right entry. But so that means that really what I can say is that the free variables, gamma could say more than things about the free variables, but it can't say less. Gamma has to have an entry for every free variable t. And then remember, typable is something t is a relation on a term and a gamma, like t is typable in gamma. We don't necessarily even care about the type. We just want to know, does gamma have enough information in it? I mean, a context is just a collection of things you know. Okay. So, I mean, obviously, if I had added over into here, you know, y has type A, then I would have had y has type A, and over here I would have had y has type A, and then over here I'd be all set. And then this is an instance of the axiom rule. Okay. Oh, and so then this has type what? B. And so this is a B. Okay. Now, eventually we're going to get to system F, which is a system, which is a you know, a typed simply, it's simply typed lambda calculus, basically. So, but the big theorem here is the strong normalization, and that is the one that says, okay, this is crazy. It says that they all terminate. So it leads to termination. It leads to a normal form. And so the term normal form is kind of a generic thing. What is a normal form? If there is no redex, and remember, a redex is a term of the form lambda x, and I don't know, a dot m applied to n. This is kind of crazy. There's no term that is well typed loops forever. It's kind of like what we want. Right? That's what we would like to have in a programming language. Now, it turns out that this is true. But since there are terms, since there are programs that since there are untyped lambda terms that can, on some reduction path, loop forever, well, so maybe I should say one thing first. Say like, type erasure. So if I have if I want to erase the types, so this is like a common way to write down a relationship. I say like, okay, the erasure of X is equal to X. I'm erasing types. The erasure of M applied to N is equal to the erasure of N, whoops, N applied to M, but I got to individually now go down inside and do the erasure inside of them. Ah, and now here's where the work really happens. It's only in the lambdas. So if I have something of the form lambda x dot a dot m, and I want to do the erasure, type erasure on that, that's just equal to lambda x dot, and then do the type erasure on m. So this is erasing types. And so now this is a way to now, one thing to notice is that the only reason the types are in there, in tags, these type tags are in there, is to help us with the rules, with the lambda rule. Because then we take the tag and we use that to say what this variable x is. But when you're running a term, the types don't play any role in evaluating a term. They're just there to determine whether or not the term, help you determine whether or not the thing is well typed. And if it's well typed, you get this amazingly strong property. No matter which way you choose to reduce a term, you will always reach a normal form. And a normal form is a term that has no redexes. And so if you take the erasure of a type, and since there are untyped lambda terms that can, on some reduction paths, loop together, we know there is a term T let's say an untyped term T such that there is no typed, simply typed term T prime such that the erasure, I'm going to need 2 lines here. The erasure of T prime is equal to T. I guess I should have stated a little lemma in here, which is that, if T has some type A, then the erasure of T is strongly normalizing. Okay, I think, are we at the end?
It's, yeah, 3 o'clock.
Yep. Okay. Questions? I mean, this is an amazing thing about simply typed lambda calculus. Every program terminates. It's not saying how long it takes to terminate, but every program terminates. So it's not Turing complete because there are untyped terms. The untyped lambda calculus is Turing complete, but the typed lambda calculus is not Turing complete because every program halts. And it's funny. It sounds like it's like why isn't everything done in the simply typed? Like why don't we just have the equivalent? I mean, we have higher order languages, but we can always translate them back down to lambdas. And so why don't we make it so that the higher level languages maybe all are equivalent to typed lambda? Then we don't have to worry about, programs that loop forever. Somehow, by not having types, it makes it possible that there are terms that you can express, computations that you can express that are not expressible in any type term. All right, I got to get running. I got an appointment.
Thank
Just
you.
one quick thing.
Yeah, sure. Yeah, Keegan, go ahead.
For the assignment that's due today,
Yeah.
there's no submit button
Ah,
on the page.
I'll try to fix that
Okay.
right
Thanks.
now. Okay. Okay, thanks.